Okay, so today is week 10, right? And today we are dealing with CNNs, convolutional neural networks. Uh, and yeah, so the basic flow of today's material will be that we'll go through some sample assignment type questions relating to CNNs, right? That will cover broadly, how how the how the CNN, like how convolutional filters act on images, what kind of effects they can produce, how they transform the input uh, image to output image, right? How the dimensions change, right? The calculation of that, things of that nature. And then at the end of the questions, I will cover, I will briefly explain some interesting details regarding how convolutional networks are actually implemented in uh, the deep learning frameworks, right? And then we will see some hands-on examples with the CNN classification, right? And some basic CNN classification on the CIFAR-10 dataset, and then we will try to improve that CNN classification a little bit by applying some well-known techniques like batch norm and dropout, right? So that's going to be today's session. And uh, we'll start off with one convolution, right, which is the it's a simpler case of convolution compared to 2D convolution. And what's happening here is basically that you are applying a 1D filter instead of a 2D filter. That's the difference, right? And so uh, because you're applying a 1D filter, uh, inputs are also going to be 1D, 2D. That's why your X here is like a single vector rather than image, right? Which is a rectangle square data. So the question here is that you're given this weight filter, right? Weight kernel for something like this 0.02, 0.03, 1.01. And the way you apply this filter is that you place it on top of the X, right? And wherever is the last filter value, wherever is the last kernel position, that's where you read out the output, right? So when you place it like this, your output will be put out over here. And then the question is what will be the output here and what will be the output over here, right? So basically, compute the output over here is already shown how you have to place the kernel. So you can just see it. For doing it over here, you need to place it accordingly in the correct position and then compute, right? So why don't so I'll just give some time for you to work it out, and then you can post the answer in the chat, right? And then a couple of minutes we will see the solution. Okay, so it's an answer. Uh, yeah, I suppose I think this is the correct. Let's see. Yes. So first one is very straightforward, right? Because they want to show the weights as they're supposed to be placed. So you just do 0.02 times this plus 0.03 times 0.9 plus 0.1 times 2 plus 0.01 times 1.6, and you get whatever 0.265. For the second case, you have to slide this window over here such that this last point, this last value of the coordinate aligns with this 1.7 over here, and then you apply the same computation, right? So you slide over here like this, and you apply the same 0.02 times 2.1 plus 0.03 times 1.7, 0.1 times 1.1, 0.01 times 1.7, you get 0.2, right? So this is how you compute it. And basically, this is uh, the the same way that you would compute the 2D convolutions as well. The only difference is that instead of having 1D kernel, you have a two-dimensional kernel, right? And slide it across the image from left to right, and then once you've reached the end, you start it again at the beginning, but you shift it down by 1 pixel, right? So you go slide like this, then like this, and so on until you have covered basically the entire image, right? So that's how convolutions work. Uh, the next question is about shapes, right? And this is uh, kind of a typical question related to convolutions, right? Uh, the, the basically will just be given an input shape, uh, filter shape, right? X and Y, height and width, basically input shape, filter shape, and amount of padding, right? Amount of padding and the stride, and the question will basically what will be the output, right? So when you apply this filter with this amount of padding, what is the shape of the output that you get? And there is no like secret uh, to this. It's very simple formula that you just have to kind of remember, right? For simple for simple cases, you can just imagine placing the filter, right? You can just imagine placing the padding and then placing the filter accordingly and try to figure out uh, how many pixels will be there in the output image. But generally, it is more much more convenient to just remember the formula, which is kind of a simple formula, and they'll give you the answer for every possible case, right? So this is just an application, straightforward application of the formula that computes the output shape, right? So if you know, you can apply that, or you can look it up into your email notes and try to apply it. I'll just wait for a minute and then we'll you'll see the answer and then move on. Okay, so yeah, like I said, there is no great secret to this. You just have to know the formula. Formula is basically n minus k plus 2p divided by s plus 1, and then you take the floor of the whole thing, right? Floor is basically if you get a fractional answer, you go to the lower integer, right? So n is the input height or width, right? K is the filter height or width, p is the padding, s is the stripe. In this case, n is 9, k is 5, and p is 0, and s is 1. So you get 5 minus 5, sorry, 9 minus 5 divided by 1, which is just 4, and then 1 plus 4 is 5, so floor of 5 is just 5, right? So you get output dimension as 5 by 1, right? Uh, so here is again another similar question, but here now we have expanded to the three dimension, like to all three dimensions, right? In general, when you use convolutional neural networks, convolutional layers, uh, your input will have basically three dimensions. One is the height, which is the number of rows of the image. One is the width, which is the number of columns of the image. And the third dimension is the number of channels. Right? So the channels basically correspond to some kind of feature dimension. Right? These are the number of features that are present in the image, in a sense, right? Per pixel concept. So yeah, so basically you have a three-dimensional input, and the convolution itself, convolutional kernel will typically have four dimensions, right? It will have a kernel height, kernel width, which are the first two dimensions. Then it will have basically the input number of channels, right, which is in this case 3, and it will also have the output number of channels, right? So the output number of channels basically is the number of features that are going to be present in the output, right? Output of this convolution. So basically, when you apply a 2D convolution for taking an entire uh, 3D grid of the input, that is kernel width, kernel height by input channels, and then you are applying the convolution weights by 5 by 3, and you are compressing all of that into one value, then you are applying it out channel number of times, right? So that's how you get, for every pixel you get out channel number of values that you generate by doing the convolution. So the output channel, this one, the final uh, dimension over here, the output channel dimension, is also often called the number of filters dimension, right? So the basic idea is that each filter is kernel width by kernel height by input channel, and the number of filters, n filters, so that many filters are going to be applied, so that many features are going to be generated for the next layer, right? So question here is pretty simple, which is that what is the output shape, and uh, the only thing you have to do here is apply the same formula that we did earlier. Assume that there is padding, right? Which I not mentioned here specifically, but um, there is no padding, uh, and yeah, uh, padding, padding, padding. So the question is, what is the output shape, right? So it should be fairly straightforward based on all the discussion that uh, I just went through.
Hello.
Yeah.
I have a question.
Yes.
Uh, so, regarding the dimensions of the filter that's mentioned, it's written 4 at last. So, does it imply like there could be 4 different filters, or is it? I mean, I'm thinking of one more condition. Like before, when let's say 4 was not mentioned, it would have taken the 3D input and map it to a 2D output. I mean, we would have got one single value.
Yeah.
And what I'm thinking was that maybe we could do 4 different operations on that one single value. Like, let's say, I mean, it's a hypothetical scenario. Like, once we do square of it, once we take log of it, and in these ways we can get 4 different values. That could also be very good for having cross 4 at last.
Uh, so that's not exactly correct. What you are trying to say is basically applying different activation functions, right? And then kind of concatenating the outputs of different activation functions, but on the same basic uh, pre-activation, right? And uh, that is fine, but I think that is not something that is typically done.
These two would be totally different things, right? If we
Yes.
take it as
Yeah. So that would be,
different filters or
yeah, that would be completely different. That would be, if we do something like that, it will be more. I mean, it will have fewer computations compared to this. It will also have fewer parameters compared to this, right? It will have one-fourth the number of parameters. uh, the only difference is that you would be applying different non-linearities, right? And if you want to explore something like this, you can always do it, but I have to say that uh, is something that the people have not explored, right? So if you want to try it out, you can by all means go ahead and try it out.
but generally we would take it as 4 different filters, right?
Yes, yeah. Generally, it is 4 different filters, and you apply the same non-linearity to all of the outputs, right?
Thank you.
So yeah, so uh, mm, yeah, so the x and y, I mean height and width is should be quite simple, right? So you just apply the same formula, and you get the basically same thing again, which is when you apply a 5 by 5 filter, you're just reducing the dimensions by 4 on each side, right? So instead of 32, you can 28 by 28, and then what you see here is that this is the kernel height, kernel width by in number of channels, that is 3. So it covers this 3, but the output number of channels is 4. So in your output, the number of channels will obviously be 4, right? So the output that you will get is 28 by 28 by 4. That's just how convolution works, right? So yeah, so moving on. So the reason why I just for a moment, the reason why I specifically mentioned this no padding uh, is that uh, if you don't mention it, then this also becomes a possible answer, right? Because if I don't mention padding, then you can imagine that uh, some padding is applied. Typically, what the padding that you apply is of two types, right? One type of padding is called as valid padding, in which case you don't apply any padding, right? The other type of padding is called as same padding, where you apply the necessary amount of padding such that the input and output dimensions remain the same, right? So in the case where you would apply same padding, your output dimensions would also be 32 by 32, and of course the output number of channels will be 4. So in that case, you would get the output as 32 by 32 by 4 if you applied same padding, right? And this is actually the more common application use case, right? Because if you don't apply padding, then it becomes a slight headache to keep track of all the shapes of the images across your network, right? And remember that you're not just doing one or two layers in the recent networks, CNN networks. You're basically dealing with like tens or dozens of layers, maybe even over 100 layers, right? And it becomes a challenge to kind of keep track of how many, what should be the size of the image feature map at any stage, right? So what people do is that normally you just apply same padding such that the, the dimensions of the feature map remain constant across the convolutional layers, and then uh, the way you reduce or increase the dimensions is by using a pooling operations, right? So you use like max pool operations, or sometimes you can use trident convolutions also, which either which reduce the size of the image by half typically. And if you want to expand it, you either use like reshape the interpolation operations, right? So resizing image resizing using interpolation, like bilinear interpolation, or you apply transpose convolutions with certain stride, right? So that's how this is typically done, right? So just keep in mind that there are two types of padding, broadly speaking. One is valute padding, which is equivalent to padding equals to 0, and the other thing is same padding, which is equivalent to basically maintaining the same shape in the input and the output images, right? Uh, yeah. So then we have uh, so like coming in the same kind of uh, uh, same sequence or chain of thought. Basically, we are talking about padding here. The question is, what would be the proper amount of padding for a convolution described in the previous question to have the same output dimensions as it, right? So in the case that you have 32 by 32 with a 5 by 5 filter and stride 1, you want the output dimensions to have the same amount of same number of rows and columns as the input. How much padding do you have to apply, right? That's the question. And padding basically is something you apply on both sides of the image and on the top and the bottom, right? So you apply it on the top, you apply it on the bottom, you apply it on the left side, you apply it on the right side, right? And typically padding is symmetric. That is to say that each of those sides you apply the same amount of padding, right? So given those uh, given those constraints, how do you apply padding? And this is once again a straightforward application use case of that same formula, right? So here output size is known, input size is known, filter kernel size is known, stride is what is unknown is padding, right? So you can basically just solve for that padding variable and you'll be done. Uh, um, see, yeah, so this is, like I said, once again, very straightforward application of the formula, right? So here, out dimension is 32, n is 32, k is 5, p is unknown, this is, right? So get, yeah, basically what you want is 2 times p is k minus 1, right? And for k equals to 5, that means p is equal to 3, right? So you need a padding of 2 pixels at the top, 2 pixels at the bottom, 2 pixels at the left side, 2 pixels at the right side, right? So that is the padding that you would apply. Essentially, after padding, your image will become 36 by 36 because you're adding 2 input, adding a 4 pixels, uh, sides and 4 pixels on bottom, top, and bottom. Right? So 36 by 36, like 5 by 5 filter on it. Output you will get is 32 by 32, right? So that's how padding works. And so this is typical example of, like I said, same padding, right? So when you apply same padding, the when you set padding equals to same, the the deep learning like framework library that you're using perform this calculation internally and finds out which padding is given, right? And it applies that padding accordingly. Right. So uh, so now we come to like some questions about uh, what effects do convolutional filters actually perform on the image, right? So there are basically two parts to this. One part is what does the spatial filter, what effect does the spatial filter perform, right? Which is whatever your 3 by 3, 5 by 5 dimensions represent. And the second part of this is what function does the input to output conversion filters perform, right? So you remember that when that in your kernel there is always a your kernel is always 4 dimensional, right? So it is kernel with kernel helped by input dimension by output dimension. The input dimension by output dimension transformation is a straightforward, fully connected network, basically, right? It's like it's just all-to-all connected kind of a fully connected network going from 1 pixel, like essentially 1 pixel in the input image, 1 pixel in the output image. Uh, and that is like further a little bit compounded by the fact that you have this spatial dimension as well. So there is a mixture of features coming across the window that is being covered by the kernel, right? And that mixture of features then goes through some kind of a fully connected network and generates the output, right? So that's what is happening basically. There are two things. One is the spatial filtering, right? And the other is the fully connected network transformation, right? And there are some papers which have essentially factorized this behavior, right? So what they have done is, uh, so the most famous, the famous paper that obvious that actually introduced this factorization as a efficiency technique is this paper called mobile index, right? So you can look it up. It's a very nice paper. Mobile index. Uh, Basic idea is was to make efficient convolutional neural networks that you can run on mobile devices, right? And what they did was they factorized this CNN operation into so-called depth-wise and point-wise convolutions, right? So the depth-wise convolutions, basically you apply a spatial filter, a separate spatial filter on each channel, right? So you apply one spatial filter on the first channel, second one on the second channel, third channel, and so on, right? So the number of input channels remains the same, but you have spatially mixed up features that are present in those input channels. And then the second uh, operation that you apply was a so-called depthwise convolution, which is a one by convolution with a one by one kernel, right? So it is a single pixel that looks at all of the input channels, constructs all of the output channels, right? So it is a straightforward, fully connected neural network that operates on one pixel at a time, right? So it looks at all the channels of that pixel and passes it through to a fully connected network and generates all the channels of the output. Right? So by doing this, uh, what they showed is that this operation, this factorized operation with depthwise and pointwise convolutions, it is basically 1 by k square times the amount of compute that would be required for a straightforward simple convolution with k by k sized filters, right? And in that sense, they made it like 8 to 9 times faster than the standard convolution operation without using much more power, right? So yeah, after that, can look this up. It's pretty nice paper. But coming back to the question here is very simple, which is that each of these kernels will actually cause a blurring of the image, right? And if you know what blurring, if you have like a simple idea about image processing, which would be fairly straightforward. Okay, so I'll just talk about this. So basically, you know a little bit about image processing. This, like I said, this question will be very simple, very straightforward, and in fact, the answer is option D, right? Uh, so in image processing, basically, it is well known that if you take a spatial windowed average of the pixel values, what you will get is a low pass filtering of those pixels, right? So basically, you'll get a blurred image. Mhm. So the key thing to remember is that uh, average leads to blurring, and differentiation uh, leads to edge detection, right? So different kinds of differentiation will lead to different kinds of edges being detected, right? So obviously, if you think about averaging, then out of these kernels, the one that will do an averaging kind of function is option 2, because you are basically multiplying each of the pixels within the receptor field of the kernel by the same value, and then you're adding up. So you're getting n times the average value pixels within the receptive, right? Yeah, so you're getting n times the average. Here n is nothing but 9, and so it's getting 9 times the average of x within the 3 by 3 window, right? So this is this, and then like I said, so in the previous section, uh, we try out a different kind of filter, right? So here it's if you see the first and the third row are uh, basically identical, but with reversed. The signs are being reversed. The middle row is set to 0, right? So the question is, what type of function does this following filter perform, right? And try to relate it to what I said earlier about the nature of operation and with the nature of like mathematical operation versus nature of what we get to see in image processing context. If you can match those concepts for uh, operation, this filter will be performed. Okay, so yeah, so this is in fact the correct answer, right? Option C is in fact correct answer, right? So remember that I said you apply averaging for learning operation, and you apply differentiation um, for age detection. So this kind of is actually nothing but a differentiation, right? It's a vertical differentiation, gradient vertical direction, because essentially what you're doing is you are multiplying pixel value at this position, you're subtracting whatever the pixel value is at this position, right? So you are taking times this, two times the same thing, and then one time the same thing here, right? And then with adding them up, essentially what you're doing is that you are computing the gradient in the vertical direction. And when you compute the gradient in the vertical direction, you find horizontal edges, right? Because at horizontal edges, the value will have a sudden shift from some value, like let's say high value to low value, or from low value to high value. In both of those cases, this filter will pick up uh, some high output, right? So it will generate some high output because you know, there is a change of value from low to high, vertical direction, or high to low, and irrespective of the sign, it will have some high absolute value, right? And yeah, so that absolute value, of course, the sign kind of determines whether the change is from low to high or high to low, but the absolute value will always tell you whether there is like a horizontal edge present with that location, right? So we just consider the action of this kernel applied on some window within within the image, and we try to think of under what situations we get a high positive or negative value. Right? Some value, some high value, some high like absolute value, whatever that may apply, right? And then if you think about it, you figure out exactly what is going to happen, right? So yeah, so these are broadly speaking a couple of uh, the operations that convolutions can perform. This is specifically related to image processing. Of course, when you go to convolution networks, uh, the functions that they perform are far more complicated and far generic, because not only do we have a spatial function, we also have a channel to channel function, right? Which is straightforward, like I said, feed forward kind of neural network, connected network, right? So here is a working example. So this is like a working example of a convolution. Uh, Basically, let's say we are given this input matrix, right? It's a 3 by 4 matrix, right? 3 rows and columns, and we're given this kernel, which is a 2 by 2 kernel. We just apply it. So just apply like value padding, in which case you don't apply any padding, and try to figure out what is the output going to be, right? So if you just work through the convolution step by step and generate the outputs, and then we can see how it is, and uh, see how the convolution proceeds, right? So this should not take like too long. I think I'll just give a couple of minutes to work it out. Okay, so
The anticipation surrounding Hightail has been
so let's just see how the convolution proceeds, right? Uh, yeah, so just of the but I'll just say what is the correct answer. So, try to compute it. So yeah, so first of all, apply place place the kernel over here. Right? The kernel is 100, which means that you're just basically adding the top two uh, pixel values. So here is like plus 3, 4. Then shift it 1 pixel to the right. Plus 6 is 10. Plus 7 is 13. Right. So now we have reached the end of the image on one side, the right. So next we go back. Like it is reset, but we shift 1 pixel down. Right? So I place it here. So it's 2 plus 4 plus 6. 4 plus 7 will give 11, and then 7 plus 8. Right? So 4, 9, 13, 6, 11. Yes. Right. So this is working of a convolution operation. Next up is working of a max pull operation, which is, like I said, a very common way to reduce the dimension of the images. Uh, Typically, what you do is that you apply the 2 by 2 max pull operation, stride of 2, right? So you apply, basically, you apply max pull on this 2 by 2 panel, then you shift two pixels, like here, then you apply here and then here, right? So that's how you're basically going to compute the output, right? So I'll just give, let's say, a minute to work out the output. Just see what it is. Right. So, like I said, uh, you just apply it right over here first, right? 2 by 2. So you apply here max pull, you get maximum value is 4. Then shift it by 2 pixels. Right here, maximum value is 8. And since you have reached the end over here, you're going to go reset it to the right and shift it by 2 pixels again because you're going stride of 2. Right? So you're playing over here. So you get maximum value here is 7. Then apply it on this final 2 by 2 window, get maximum value is 11, right? That gives you 4, 8, 7, 11. It's just how you apply, right? Well, then, uh, yeah, so this is the end of the questions that we're going to discuss. Now I'll briefly talk about the implementation, right? So we have seen here how a convolution operates, right? So we have seen this thing, right? And the question now is that, is it really, is the convolution operation actually performed like that? When you do a convolution operation using like a standard Euclidean framework, right? So if you're using PyTorch or TensorFlow, heavy, if you apply the convolutive operation, uh, is that is that actually what is happening? The answer is not really, right? And I will demonstrate what actually kind of happens through a somewhat simple example. We will take a input image that is a single channel, right? So this is a single channel input. We will consider, let's say, a two channel output, right? So you're going from n by 1 to something. So let's say 3, we are applying a 3 by 3 filter, so n by n minus 2 by n minus 2 by 2. Right? So that's what you are doing. And basically, the basic idea here is that when apply when you call the convolution operation, what it does is that it applies, it kind of scrambles these image pixels uh, in a way that uh, performs that kind of performs the convolution operation, right? So performs the scanning part of the convolution operation, right? So basically, you would start over here. So you would start at this position, and you would have all of these, you know, 9 inputs that you are going to use for the first pixel of your output, right? So you grab all of these 9 and then you vectorize it, right? You make one single column. So this is your first column, right? Then you shift your filter 1 pixel to the right. So you have this dashed, this filter location showcased by this dashed blue light, right? Blue boundary, and you grab these 9 pixel values, right? And you put them on, okay, convert them into a column like this, right? Or you convert them into a vector, right? So you put this is your second vector, and then get another, move it 1 more pixel, you get another vector, and so on until you reach the end of here. Then go, you know, go down, grab these 9 pixels, right? So these 6 plus 3 that come below them, you grab those 9 and go again to the right and so on, right? Essentially, what you're going to do is that uh, this n by n input is going to be converted by this scheduler into a n by 2 square uh, vectors, right? So there will be n by 2 square vectors, and each of these vectors will be of size 3 by 3 by 1 in this case, right? Because in this case, we are considering a single channel input. So each of these vectors will only be of size 9, right? In the case where we are considering multiple channels in input as well, so these vectors would be of the size 3 by 3 by input channel, right? So they'll just be much longer, right? So yeah, so you basically have n minus 2 square uh, such vectors, right? And each vector being of size whatever, kernel size by input channel, right? And then you take all of these vectors, and the second step that you apply is that you convert the kernel, right? In this case, we had a two-channel kernel, right? So each of the filters is a 3 by 3 by 1 filter because input has just one channel, and then the total kernel is 3 by 3 by 1 by 2, right? So you have two of those filters over here, right? And then what you do is you convert these filters also into like into rows or matrices or whatever, right? So convert them into a matrix, a weight matrix, right? In this case, the first row basically is your the first row over here, which is like you can see is your uh, first filter, second row is your second filter, right? And then you perform matrix vector multiplication with this and all of these vectors, right? So you perform when you perform this matrix multiplication. So this matrix is 2 by 9, right? So it's a 2 by 9 matrix, and this is a 9 by 1 matrix, a 9 by 1 vector, each of this, right? So this matrix vector multiplication will generate two values, which are your two channel outputs for one particular pixel in the output, and the second will generate another two values, which will be your channel outputs for that particular pixel position and so on, right? So basically, uh, what happens internally is that the convolution operation is converted into a large matrix matrix vector product kind of operation, right? Which is a straightforward standard, typical like uh, feed forward layer or linear layer operation, right? And the reason that it is done like this is because this kind of matrix vector products, uh, they are highly optimized, right? So there are all of these like advanced libraries, advanced like linear algebra libraries that perform this matrix vector product in highly optimized way. Right? So this is extremely fast, right? And that's how this process carries on. If you were to do the convolution naively, which is like you apply the filter again and again, shift and then multiply and add, that will be a very, very inefficient way to do it compared to uh, something like this, which is not only is it very optimized, but it is also extremely parallelizable, right? So you can basically run all of these operations in parallel, right? Because if the output of one of these matrix vector products is independent of the output of all of the other matrix vector products. So you can basically partition them out into different like threads, and then just compute them parallelly and re, uh, re recreate the output and put together all of the outputs back once everything is finished computing, right? So yeah, so those are the reasons why we do this. And if you want to look into it in a little bit more detail, uh, the operation. So this scrambling operation that I have described here is typically referred to as into-call, which basically converting images to column vectors, right? And which is exactly what it is. It's taking this image and it is converting it into column vectors in such a way that the convolution operation can be applied simply as a matrix vector product, right? And uh, one side effect of this elliptical, this kind of um, implementation of convolutional neural networks is that the uh, factorization that I had earlier talked about, right? The depth-wise and point-wise factorization that I have earlier talked about becomes even more efficient with this framework in mind, because the pointwise convolutions, right? So pointwise convolutions, for pointwise convolutions, this integral operation is very, very simple. Basically, you're just picking one pixel at a time, and you're just taking all of those channels and placing them as a column, right? So your image is almost essentially pre-converted into this integral format, right? So you don't really have to do anything, any kind of processing here, right? So it saves a lot of processing on the depth-wise convolution part, which actually turns out to be the heavier operation. Uh, sorry, it saves a lot of, it saves some processing on the pointwise uh, convolution part, which actually turns out to be, like I said, the heavier operation out of depthwise and pointwise convolutions, right? So, yeah, so this is internal implementations of CNNs, and finally we are going to see an example CNN CNN network application, right? 9-layer CNN for CIFAR 10 classification. CIFAR 10 is a kind of an old image classification benchmark that has 10 classes basically, right? Airplane, mobile, bird, cat, dog, frog, horse, truck, right? And each of the sample images are 32 by 32 color images, right? So they are small, but they are color images. So it's 3-channel, right? So we'll do this. We'll do the CIFAR classification with a 9-layer CNN. So CNN uh, structure kind of looks like this. So we have first input row is by 3 channel input because it's colored. So we convert it to 32 by 32 by 96. So this is 96 channels. This is convolution with same padding. But again, 32 by 6. Then we apply convolution max pooling. So you go down to 16 by 16, 96, then you expand the number of channels. Right? So this is a typical strategy that you will see in convolutional neural networks, which is that you have some number of layers with the same number of channels, right? And then you go down the size, right? So you reduce the size by half in both of the dimensions, and then simultaneously you double the number of channels, right? So here you go from 32 to 16, and then you double the number of channels to 192, right? So then again, you have some blocks with 192 channels. Then again, you go down from 16 by 16 to 8 by 8. And in this case, we don't increase it any further. Right? So we just maintain 192 channels. Have again few uh, convolution layers with 192 channels. And then what we do here is we bring this 190 to compress this 190 channels to 10 channels. Here we apply some sort of, so here what we do is we basically flatten this out, right? Uh, yeah, so here essentially what we're doing is we're flattening this out. We get 640 size vector, and then we have like the 10 output classes, right? So that's broadly the structure of this network. Let's see. Okay, so let me share this screen. Yeah, so we will see basically two variants of this network. Right? First one is the basic variant where we just have the network, right? And second one is going to be slightly improved variant of the network where we're going to add, we're going to add batch norm as well. Right? How that improves stuff, right? So here, uh, straightforward stuff start. So we'll just import. So here In all of the previous example notebooks that I have shown, I believe they're typically they typically have been all TensorFlow examples. Here I'm going to break with that convention a little bit, and we're going to do PyTorch. So, yeah, first thing is always just importing stuff, importing the libraries. Then we generate this model, right? So it's called the all CNN model. Basically, is entirely convolutional network except the final output. So, we have three CNN layers per block. Then you have a max pool operation. Then you have again three CNN layers in a block. Another max pool. And you have again three CNN layers in a block. Then yeah, and then you apply flattened linear. Fairly straightforward. Uh, so in PyTorch, basically, you define your models as like inherited from this NM module class, right? And basically, there are two functions that you have to define, right? Two functions that you have to define are this init function, which is basically builds the model, right? Or rather, it does not build the model, it basically creates all of the components that will be part of it, right? So in this case, I create like prelude, which is my activation. Create all of these 9 convolutional layers, right? And I create this max pooling layers, this flattened layer, and the fully connected out layer, right? So this is the final output. And then the second function that you have to define is this forward function, which basically tells the compiler whatever resources is running this program, uh, how this model is supposed to run, right? So it connects all of those components together that you have already defined in the init function, right? So here you define the forward, which basically, yeah, it just goes through all of those layers, right? So you apply one, two, value, so convolution, value activation, then second convolution, third convolution. After the third, you apply max spool, then again three convolutional layers. So when you apply the second max spool, then again three convolutional layers. Then you apply the flattening layer, and finally you get output. Right? So you apply fully connected FC output. Yeah, it's linear. Right? Uh, okay, so we have GPU here. Here I'll just grab the summary of this model. Uh, 310. So this model that I have defined, it takes two inputs, two kind of parameters that as the input, which is in channel and out size. In channel is the number of channels in the input image, which we know is 3 or CFR10. Out size is the number of classes that we have to classify into, right? So this, yeah, and this gives us a summary. Summary basically gives us a summary of the model. Here, uh, most of the parameters are summed here because we're going from 192 dimensions to 192 dimensions, right? Solution plus one Uh, yeah, so final linear layer has 1,400 parameters. This one is going 192. Okay, okay, I see. So the last two convolutions are one by one convolutions. That's why this convolution has fewer parameters compared to this one. Then the last one is going for 190, 10. So, right, so that's why. Sorry. So then define a function. So this function basically computes the test accuracy given a data loader and a network. So it puts the network in eval. So this is important. When you're testing your network, you have to put evaluation mode. So basically, when you run evaluation mode, it does not compute the gradients and it doesn't update all the parameters, right? The weights of the network. Then these are fairly straightforward. Boilerplate code, right? And then finally, so this here is the train model, the main code that runs the training. Uh, First of all, you basically have to get the data. So, but so for train test uh, data sets is like 10, and yeah, train part or test part, and uh, train and test transform is these are different transforms that you apply. Here we are applying some data augmentations, right? So data augmentations are random horizontal flips where you take an image and just randomly flip it in the horizontal direction, right? So it's like taking a mirror image to the center part of the image, right? And then the other part is a random crop, which is just cropping the random part of the image, right? So this kind of synthetically generates more data for the network to train. And then finally, you normalize with this normalization uh, values, basically normalizing the colors that are present uh, in your images. So for the test transform, you don't need to apply obviously data annotation, you just perform normalization. Right. So the train loader, test loader set the in channel and out size, and uh, create the model over here. So so we have created so create the model over here. And we also create like test model separately. Yes. In channel out size, set the optimizer as the atom optimizer. Uh, Atom optimizer has to be sent list of the parameters that it has to optimize. Right? So you send this model dot parameters, which is list of the parameters. And that function is set as cross entropy loss because there's a classification, right? Frame, so obviously for training, frame, and right. I see. So yeah, so you compute the test accuracy and loads test. Okay, it doesn't matter. It seems to be the same thing. Let's run this training code. Yeah, so this has now generated uh, the data loaders, run the training part of the outputs. Right. So it has already started. Uh, yeah, this is happening twice because we are running it twice. here some risk, but essentially it's the same hardware, right? So this is going to run for 10 epochs like this. I've set the number of epochs. It's 10 and get some output. Meanwhile, let's see the modification. Right? So most of it is same. The major difference is of course here, right? The model definition. These are additional parts, right? So all of these batch norms, right? So batch norm 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 batch norms corresponding to the 9 convolution layers, right? What corresponding to each convolution layer. Just like we have convolutional layers, we have 3 convolutional layers, output 96 channels, and we have 6 convolutional layers, which output 5, I guess, and convolutional layers, which are 192 layers channels, and then one that outputs 10 channels, right? Um, then the difference here is that we apply the convolution, then you apply batch norm, then you apply FRELU, right? One thing important to keep in mind is that you should not apply batch norm after convolu or after ReLU, because ReLU will only be, because batch norm is basically, the idea behind batch norm is to somehow correct the statistics of your output, right? So you should not apply it after ReLU, because ReLU will already skewed out the statistics of your output, right? Because it will kill everything that is less than 0. So apply batch norm immediately after the convolution, then you apply the operation. So get one batch norm 2, 3, then next 3. So these are basically 192, 194, 5, 6, right? And then 7, 8 size, just one here. So the ninth convolution size is outside. So that's the channels in the batch now, parameters in the batch now. So no, outside. So and uh, yes, the rest of all is exactly the same. Let's see how well that performs once this has completed its plan. It's currently ninth epoch. I think there will be one more epoch for this. Then you can see that performs. Okay, so this is done essentially. Yeah, so this code is done with writing. As you can see, in 10 epochs, it has reached 78% specification accuracy on the test, right? 2% test accuracy. And now we'll see the effect of attachment, right? First, import style. Okay, this is the check summary function. Find it. Okay, okay. Here you will see that now we have this batch norm layers as well. Uh, in this case, you will say batch norm does not have any parameters, does not have any learnable parameters, and the reason why is because I have set this affine equals to false, right? So if you remember your batch norm session, right, batch norm classes where you discussed, or the batch norm was discussed, you'll remember that we can learn these scaling and shifting parameters, right? Alpha, beta kind of thing. Um, for scaling and shifting the batch output. And if you want to learn those parameters, you set affine equals to true. If you don't want to learn those parameters, you just want to apply batch norm, right? That is to say, if you just want to apply this normalizing operation where you create, where you generate outputs with zero mean and unit variance, in that case, you can set affine equals to false, right? Even this, as you will see, generates a significant improvement. Of, so, yeah, so it's a strategy, couple of approaches, right? I mean, consider this, this beginning with this uh, significant head, will also end up uh, significant head by the time it finishes. With so, about 6 minutes. So this should also take about same amount of time. Okay, so see, yeah, so this is something, I mean, this is kind of common, right? Uh, Trading is a little unstable, looks like, but uh, as you kind of expect, you know, the best performance that you were able to achieve with patch now significantly be better than what you were able to get without patch now. You can try all kinds of other uh, regularizations as well, like simple batch nodes are fine to true. You can try trace, dropout, other things. You can try I think should apply some sort of L2 regularization in the that will help, but generally helps, right? So yeah, so this is kind of like the basic introduction. So this was like basic introduction to convolutional networks, right? Uh, there are a bunch of papers. People are interested in uh, studying more convolutional networks. There are a bunch of papers that I would suggest writing. Papers number one is ResNet paper. Is received to right? So this is a very famous paper. This was the winner of ImageNet challenge, right? Then, like I said, there is mobile nets, right? So mobile nets, nets, V2. So these are efficient, efficient implementations of convolutional neural networks or resource constrained devices, right? These are typical ones, but once you read the paper, you'll find out, you'll basically find more and more variants of these things, right? Then shuffle. Then there is a bit called YOLO ones. So this is uh, one shot, one shot object detection. This is a pretty good uh, paper, right? So ResNet talks about standard kind of network architecture that is very common even today, right? When uh, these large language models are actually kind of built up on top of this residual architecture, right? So that's how influential this paper is. Uh, then mobile nets and mobile nets V2, this kind of kicked off the idea of creating uh, networks for resource constrained devices, edge devices, right? Then YOLO is pretty uh, influential as well, right? It's basically the state of the art in object detection and localization. It has been for like almost 11 years at this point. So they have launched 11 versions. I think the latest version of YOLO is YOLO V12, V11, something along that line. But yeah, it's one of the best papers. It's a very good paper to read, right? Because it goes into uh, all kinds of, to me, it's very intuitive paper. But yes, these are some of the papers I would suggest reading. A little bit more math intensive would be GANs. I'd say that GANs. So one paper called Pigs to Pigs. which is a conditional terms. So look, these papers as well. And broadly speaking, we're studying deep learning of three papers. Uh, So yeah, I think that covers today's material, that whatever I wanted to cover. Picture. So if you have questions, you can ask now. Otherwise, free to leave the call. Okay, there doesn't seem to be any further questions, in which case I will end the call.